Good morning. So today we're going to continue with the ideal gas law, and then we're going to look at an application of the ideal gas law. So let's remind ourselves about the previous lecture, where we said that for gases, we can develop what's called an equation of state. And in this context, we don't mean state as in like solid, liquid, gas. We mean the properties of the gas. So the idea would be that suppose you had a gas which is inside of a cylinder with a piston. Okay, so here's your gas in here. And that gas has some pressure, some volume, and some temperature. What we'll claim is that if we know these three, we can also find the number of moles of the gas, so we can determine what the number of moles are. Okay. So that means that we have these properties that we can measure that will help us describe how the gas behaves. Now, suppose we undergo some sort of change. Okay, suppose, for example, we heat the gas. We add a little Bunsen burner, some sort of flame to it, right, to the cylinder. Well, it's going to heat up the gas, right? And then the question is, well, what happens to the gas? Well, let's suppose that what happens is, the gas expands. So we're adding heat, the gas is getting hotter, the volume changes. The amount of gas maybe in this condition isn't going to change, and perhaps the pressure won't change. But in any case, we will now have a new pressure, volume, temperature, and number of moles, a new set of values once we've undergone this change. So the state, the conditions are now different. So if that's the case, we'll go ahead and number them. We'll call all these 1 for initial, and we'll call all these 2 for final. Okay. And what we would say is that there are multiple equations out there. Actually, there's lots of equations that we could develop, but there is at least one equation of state, an equation that describes this change, how the pressure changes, how the temperature changes, how the volume changes, or doesn't change for that matter. And so one of them is called the combined gas law. And so that one would be P1V1 over N1T1 equals P2V2 over N2T2. And another one, which is related, is called the ideal gas law. And that one is PV equals nRT. So notice the form of this one is different, right? So instead of having initial and final, we just have the pressure, the volume, the moles, and the temperature. R is a constant, which is called the universal gas constant. 2057338, I think is what I said yesterday. If we went out that many units. And if we went out that many decimal points, and it has a lot of units in it. Okay, so that's called the ideal gas law. So these are both the combined gas law and the ideal gas law are both equations of state. They describe how the properties of the gas will change under certain conditions. Now, let's take a look at a problem involving the ideal gas law. This is the second type of problem we're going to do. And it's called interconverting molar mass and density of an ideal gas. So an ideal gas is a gas that obeys this equation of state, the ideal gas law. calculate to 3 significant digits the density of carbon monoxide. So carbon monoxide at exactly negative 10 degrees Celsius and exactly 1 atmosphere. So they're telling us that we should not consider 10 degrees C to have 2 significant digits, and we should not consider 1 atmosphere to have 1 significant digit. They're telling us these are exact values. Okay. You can assume that carbon monoxide gas behaves like an ideal gas under these conditions. Okay. So it turns out the ideal gas law is not a perfect law. You know, it works for most gases, not all, and only under certain conditions. So if the pressures are very, very large, if you have pressures of 20, 100, 200 atmospheres, the ideal gas law breaks down and you have to use other equations of state that are more complicated. Same with temperature. If the temperature is very, very low, let's say it was like 10 Kelvin or 5 Kelvin, assuming that the substance you're looking at is still a gas, it will probably deviate from the ideal gas law, and the combined gas law not work very well. So again, you have to use another type of equation of state. And there are more complicated ones that you learn in physical chemistry if you go on and take that. Okay. For us, we're just going to focus on the ideal gas law. So notice we're given the temperature, we're given the pressure, we're told it's carbon monoxide. So from that, we can figure out the formula, and then it asks us for the density. And it turns out there's a relationship for the ideal gas law that relates the molar mass of a gas to its density. So let's take a look at that. Let's take a look at this relationship. So this is the relationship between density and molar mass of a gas. Only works for gases, just like the ideal gas law. Okay, so here's our ideal gas law. Right, PV equals nRT. P is the pressure of the gas, V is the volume of the container, N is the number of moles of the gas, R is a constant, and T is the temperature. Okay, now we're relating this density and molar mass. So density, what's the definition of density? Well, it's the mass of a substance divided by its volume. And what's the molar mass? Well, often at this stage in the course, people recognize how to calculate the molar mass. They just go to the periodic table and add up the atomic masses, and they've got your molar mass of the compound. But by definition, the molar mass, which I'm going to use a capital M that's in script, a script M, is the mass of a substance divided by the number of moles of the substance. Okay, mass over moles. So we have these 3 equations here: molar mass, density, and then the ideal gas law. And what I'm going to do is I'm going to use these 3 equations and I'm going to modify the ideal gas law. So one way to do that is, if you take a look here, how we have moles in here in the ideal gas law. What I'm going to, I'm sorry, we'll do that second. Let's focus on volume first. We have volume right here. The volume is also in the density equation. So if we rearrange the density equation to have the volume on the left side, it would be mass over density, right? Volume would be mass over density. So I'm going to substitute that in there. So now I'm going to get PV equals nRT is now going to be P times M over D is equal to nRT. Okay, that's called substitution, right? We do that a lot in the algebra. Okay, so then we also have this relationship that involves moles here. See how we have moles here in the molar mass? And then we have moles in the ideal gas law. So I'm going to rearrange the molar mass definition to have N over molar mass. Mass over molar mass, sorry. Just trying to do a cursive or a script M, okay? And then I'm going to substitute that in. So now I have P times M over D equals M over cursive M times RT, right? 2 substitutions so far. But notice you have mass on both sides. So I could divide both sides by mass and simplify it. So now I would just have P over D, pressure over density, is equal to RT over molar mass, right? Just kind of clean that up a little bit and looks a bit nicer. And, this equation is very useful because what it does is it relates the pressure of a gas to its molar mass and density. And it does depend on the temperature. Notice volume is now gone and moles are now gone. So it doesn't matter what the volume is, doesn't matter what the moles is. The relationship is between pressure, density, temperature, and molar mass. So it's not uncommon to rearrange this into two forms. So the first one is in terms of density. So if I take the reciprocal of both sides and then multiply both sides by P, you get that the density is equal to P times the molar mass over RT. All right. Is that right? Did I get that right? Molar mass grams. Yep, that's gotta be right. And then the other way would be to have it in terms of molar mass. So if I take the reciprocal and then multiply both sides by RT, you get P RT over D. Oops, sorry. Here, let's go through this. P times molar mass is equal to DRT. There we go. Okay, so molar mass would be DRT over P. I have to do that in 2 steps. Okay, so these are 2 forms of the equation. It's the same equation, right? We just rewritten it. And these are written in such a way as to allow us to calculate the density from the molar mass. So if we know the formula for the compound, in this example, we know it's CO, right? Carbon monoxide. So if you know the formula, you can just calculate the molar mass. And then if we know the pressure and the temperature, which in this particular problem we do, that allows us to calculate the density. Alternatively, if we know the density of the gas, so for example, if they say, hey, there's 1 gram of this gas and the volume is 200 milliliters, well, that's mass over volume. That gives you the density. So if you know the density, you can then calculate the molar mass, right? Again, assuming you know the temperature and the pressure. If you calculate the molar mass of a gas, you might actually be able to determine what the gas is, because remember, every compound has its own specific molar mass. And so if you find out, for example, that the molar mass is 44.01 grams per mole, good chance that's carbon dioxide. If you get 32.00 grams per mole, good chance that's oxygen gas, right? So measuring the density, we can measure the density of something, right? All you need to measure the density of any substance is know the volume and to know the mass and volume. That gives you the density. Temperature, a thermometer, right? Will tell you the temperature. Pressure, we have different sensors for that as well. Okay, so those are the 2 working equations that you can use to do this problem. So coming back to it, they tell us that it's carbon monoxide, right? They tell us that it's carbon monoxide. So calculate the 3 significant digits, the density. We want to know the density of carbon monoxide. Well, carbon monoxide is CO, carbon C, monoxide O, CO. They give us the temperature, there's your T, and then they give us the pressure, there's your 1 atm, right? Remember, temperature needs to be in Kelvin when you do any of these gas law problems. So all we're going to do is we're just going to use that equation, which is molar mass is DRT over P, and you're set, right? That's all you got to do. Molar mass is D. Oh, actually, we're trying to find a density, so I'm sorry. So it's going to be the density is P molar mass over RT. Okay. So the density of the gas is P times molar mass over RT. I'm going to do the dimensional analysis because I go through these equations quite a bit every semester, and sometimes I get the equations mixed up in my head. Maybe it's really, RT over P molar mass. So what I'll do is I'll do a little dimensional analysis with this problem, and that'll help us, okay? So they said make the pressure exactly 1 atm. So it's 1 atm, but that's an exact value, which you can't really do that, but in any case, that's what they're just saying to do. It's carbon monoxide. What's the molar mass of carbon monoxide? Carbon is 12.01. Oxygen is 16.00. So it looks like you get, what, 28.01. And then that would be grams per mole. That's the molar mass, right? Divide that by R. Now, R has a lot of significant digits. 0.082057338, I think. And then liter atmosphere. Sometimes I write it atmosphere liters or liter, it doesn't matter. 2 times 3 is the same as 3 times 2. And then mole Kelvin. In multiplication, units commute, right? And then you've got the temperature, which is -10. So -10 plus 273.15 is 263.15 Kelvin. Remember, it's got to be in Kelvin. Now, looking at this, I've got a lot of significant digits, but they told you to make the temperature and pressure exact values. But then they said to round it to 3. So I'm not sure what their logic behind rounding it for 3, because the R has more than 3 and the molar mass has more than 3. In fact, I use the rounded values of the molar mass, right? You could actually use for carbon, you could use 12.0107, and for oxygen you could use 15.9994 and have even more significant digits, but they said they just round it to 3, so we'll do that. So atmospheres cancel. Now I'm doing the dimensional analysis because I'm often, I get these things mixed up in my head. What do these equations look like? There's a lot of variables there. So it's density, so we should have mass over volume for the units. So mass doesn't look like grams cancels. It does look like mole cancels, and it does look like Kelvin cancels. So we get grams per liter. Good. That looks good, right? Mass over volume. So that means I probably got this equation, this formula right. Okay. So grams over liters. Okay, now we just got to do the calculation. 1, we can ignore the 1, right? So 28.01 divided by 0.082057338 divided by 263.15. And it looks like it's about 1.30. 297 is 30. All right, there's your density. Now, I want to point out, be careful with these density interpretations, because we are often used to dealing with density in grams per milliliter or grams per centimeter cube, right? Same unit. So the density of water, for example, at 4 degrees C equals 1 gram per milliliter, right? So you might be tempted to think, oh, well, this is more dense than liquid water, but that's not true because it's gram per liter, it's not gram per milliliter. So really what we're saying when the density is 1.0 grams per milliliter is you're saying if you have this little volume and it's water, it's 1 gram in a milliliter, right? Now it's per liter. So what we're saying is this gas has 1,000 times the volume of what we had over here. 1,000 times. It's much bigger. And that whole thing has a mass of 1.30 grams. Okay, that's in a liter. So this is by no means as dense as this one is, right? This is a gram in a tiny little space. This is a gram in a huge space, a liter, okay? So gases are generally less dense than liquids, although you could be confused, misled by comparing those numbers. That's why our units are important right here. We have to consider what our units are. So if you wanted to put it per milliliter, we just say 1 milliliter is 1 times 10 to the minus 3 liters, right? Milli is 10 to the minus 3. So you'd say 1.30 gram per liter. and then 1 times 10 to the minus 3 liters, right? So you want the liters to cancel over a milliliter. So you'd be multiplying that by 10 to the minus 3, and you have 0.00130 grams per milliliter, right? So now you can compare it to the water. The gas has a density, this carbon monoxide has a density of 0.001 as opposed to 1 for liquid water. Okay, so there you go. So there's your, that you got this equation. These problems are pretty straightforward. It's really just the ideal gas law. You got D equals PM over RT. And then you got your molar mass equals dr. This one I tend to remember because it's only got one thing in the bottom. At dRT over P. So, if they give you the density and then they ask for the molar mass, you can use that form of the equation. Okay. Alrighty. So that's our sort of intro into the ideal gas law, PV equals nRT. This is, it doesn't look exactly like PV equals nRT because it's been modified via density and molar mass. But it is essentially the ideal gas law just manipulated. So now what we're going to do is we're going to look at a problem where we, use the ideal gas law, but from the perspective of chemical reactions. So I'm going to show you a problem here. It says solving for gaseous reactant. Okay, very common type of problem when we deal with the ideal gas law. Ancient Romans often built out of bricks and mortar. They also used concrete, interestingly. A key ingredient in their mortar was quicklime, which is calcium oxide, CaO, which they produced by roasting limestone, which is calcium carbonate. Okay. Write a balanced chemical equation, including the physical state symbols for the decomposition, right, of solid calcium carbonate into solid calcium oxide and gaseous carbon dioxide. Okay. So they're telling you the reactants and products, and then they're saying, hey, balance the equations. That's your first step. Step 2, suppose that 64.0 liters of carbon dioxide gas are produced by the reaction at a temperature of 270.0 degrees C and a pressure of exactly 1 atm. Again, that exactly 1 atm is saying don't consider the pressure in terms of your significant digits calculation. Calculate the mass of calcium carbonate that will have reacted, and then round your answer to 3 significant digits. The volume is 3, so that kind of makes sense. Okay. So we're going to use the ideal gas law, and we're going to use the balanced equation to interconvert reactants and products. In general, when you talk about a solid, the amount of the solid that you use in your calculations is mass, right? Because if I have a solid, I can just very easily put this on a balance or scale and weigh it, and that tells me how much I have. So you use mass and molar mass for solids. For liquids, it's a little trickier. It depends. If it's a solvent like liquid water or alcohol, then we might use mass as well. Or we might measure the volume of a liquid and then use its density to find the mass, and then do the mass and molar mass to the calculation. So we did that in chapter 4. In chapter 10, now we're talking about gases. It is more common with gases to not weigh the gas, but to measure its volume at a given temperature and pressure. And then you can use the ideal gas law, PV equals nRT, to find the number of moles, right? So remember back in chapter 3, we talked about how you got to get the moles from the mass. And then in chapter 4, we said you got to get the moles from the molarity and the volume. And then now in chapter 10, you're trying to get the number of moles from the pressure, volume, and temperature. Okay, so we calculate moles differently depending on what the state of the matter is very often. It doesn't mean you can't do mass and molar mass of a gas. You can do it. In fact, we just saw that with the previous problem, density and molar mass. But in general, if you're talking about a gas, you're going to use the ideal gas law. Okay. So let's look at this question again. I'm not going to talk about calcium oxide and all that kind of stuff. It's interesting, history of these substances. Write the balanced equation, including physical state symbols, for the decomposition of solid calcium carbonate, CaCO3, into solid calcium oxide, CaO, and gaseous carbon dioxide, which is CO2. And then you're going to do your little calculation. Okay. So we're talking about calcium carbonate. It's a solid. So that's calcium. And then what's carbonate? Carbonate is a polyatomic ion, right? It's CO3. Which is called limestone. Well, limestone is calcium carbonate. The chemical formula is calcium carbonate, but limestone is a mineral, right? Decomposes into quicklime, which is calcium oxide. So decompose goes into, it has to be at high temperature. So you're going to put a little delta symbol here for high temperature. You're adding heat. Calcium oxide, CaO. And then that's a solid also. That's your quicklime. And look at the other products, CO2. So this is actually an issue in terms of cement production. You get carbon dioxide out of it. Okay. It's already balanced. So this one's pretty simple. You don't have to balance it because it's already balanced as it's written. Okay. But now let's get down to the calculation. What they're doing is they're telling us something about the gas, 64 liters. So they're giving us the volume of the gas. They're giving us the temperature of the gas. And they're giving us the pressure. Now, if you think about the ideal gas law, we already know that R is 2057,338 atmosphere liters per mole Kel. So we already know what K is, right? I mean, what R is, that's a constant. The only thing left is N. We don't know what N is, okay? So then they say, hey, calculate the mass of calcium carbonate from the reaction. Now remember, in a chemical reaction, you can figure out how much reacted from the amount of product you get, right? That's stoichiometry back from chapter 3.6 and 3.7. So same thing here. What we're going to do is we're going to use this information about carbon dioxide to figure out how much calcium carbonate. So our strategy is 1, find the moles of CO2 reacted. I'm sorry, produced. And then 2, find the moles of CaCO3 that reacted from the balanced equation. That's what we did back in chapter 3. And then step 3, convert moles of CaCO3 to grams of CaCO3. GMS for grams, okay? Just like we did back in chapter 3, just like we did back in chapter 4 with titrations, okay? So we have all this information about the CO2, which is a gas, and you can only use that information for gases. The ideal gas law does not work for solids or liquids. So PV equals nRT. So this is referring to CO2. So N is PV over RT, right? You just divide both sides by RT. So I'm not going to go through the dimensional analysis because it's pretty obvious it'll come out to moles. So 1 times 64.0 over, now you got to add that 273.15 to the 270. So what is that? 543.15, right? And then you got your R. Now I'm doing the T and then the R. I'm sorry. I guess I'll put the R in there so it's not confusing. 0.082057,338. And then your T was what, 543.15. Okay. And that's going to give you your number of moles of carbon dioxide gas. So 64.0 times 1 divided by 0.082057338 divided by 543.15. And it looks like about 1.44. I'm going to keep some extra sig figs, 1.43596. And this would be moles. Does that make sense? Yeah, it's a pretty high temperature and 1 atmosphere, and your volume's pretty large. So yeah, that's about right. So at STP, which is 1 atmosphere and 0 degrees C, 1 mole of a gas occupies 22.41 liters. That's a number to remember, 22.41 liters. STP stands for standard temperature and pressure. And standard temperature and pressure is 1 atmosphere of pressure and 0 degrees, or 273.15 Kelvin. So what I did in my head was I said, oh, does that answer make sense? I mean, how do you know, right? You got all these numbers. Well, I said, hey, at STP, 1 mole would occupy 22 liters. Well, this is more than 22 liters. This is 64 liters. So presumably at STP, it would occupy, more than 1. I mean, it would be more than 1 mole. 2 moles would be twice as much, which is 44. 3 moles would be 3 times as much, which is 66. But, you have to be careful because the temperature is not 0 degrees C, it's 270 degrees C. So that's going to make your answer. But it at least told me that it seems like it's reasonable, it's possible. Okay. What you can do just to check, so again, like I like to check myself. If I take 0.082057,338 and multiply that by 543.15, I get 44.57 down in the denominator. So 64 over 44.5 is going to be a little bit more than 1. So again, it sort of checks out. It's a little bit more than 1. So that seems reasonable. Okay. Now, here's the next step. Step 2. Find the moles of CaCO3 reacted. The way you do that is through your coefficients, through your balanced equation. This is what we did back in chapter 3. So you take your 1.43596 moles of CO2 and you say, look, every time one of those was produced, one of these reacted. 1 mole CaCO3 reacts for every 1 mole CO2 produced, right? And so now you get the same number. So just be careful with these. You might get the right answer in these calculations, but not actually know what you're doing, right? We have to do that step because that's telling us how much CaCO3 reacted as opposed to how much CO2 was produced. And now we can just convert it to grams. Step 3, just convert it to grams. So you take your 1.43596 moles of CaCO3. I'm going to multiply by the molar mass. Calcium is 40.08. Carbon is 12.01. And then oxygen is 16, but there's 3 of them. Yeah, 100.09. Right, that's the molar mass, 100.09 grams per mole. So it's going to be a pretty good size mass. It's going to be over 100 grams. So that times 1.43596 looks like they said to do it to 3 significant digits, so 144. All right, so look what we did. We just figured out how much calcium carbonate has to react to form this carbon dioxide, where the carbon dioxide is a gas, and we had to use the ideal gas law, and the calcium carbonate is a solid, so we had to use its molar mass. So that's kind of cool. Like you're now starting to do some pretty sophisticated calculations here, right? You're like, well, this is a gas, so we're using the ideal gas law. We're looking up a constant. We're manipulating it algebraically. And then on the reactant side, it's a solid, so we're doing, mole to mass calculations, and we're using this balanced equation in order to figure out the relationship between the reactants and the products. Okay, so there's a lot in that. So let me do one more. Okay. Solving for a gaseous reactant. The great French chemist Antoine Lavoisier discovered the law of conservation of mass in part by doing a famous experiment in 1775. In this experiment, Lavoisier found that the mercury 2 oxide, when heated, decomposed into liquid mercury and an invisible and previously unknown substance, which is called oxygen gas, right? So he's the one that actually discovered. So you can do this. You can take these, we used to do it in the laboratory for this course. You take these oxide solids and you heat them and they decompose and produce oxygen gas. And you can collect the oxygen gas and you have purified oxygen and you can do all kinds of cool stuff with oxygen, okay? So write the balanced equation and then again, do a calculation. They're going to give you the volume, the temperature and pressure of the gas, and then you're going to find the mass of the mercury 2 oxide, okay? So let me show you this one too. Okay, so it's mercury 2 oxide. Decomposes into mercury, which is a liquid. So this is a way to get liquid mercury too, and oxygen. Okay, all right, so mercury, the symbol for mercury is Hg. Hydrium, I think it's called, right? It's Latin. Now it says mercury 2. What does that mean? That doesn't mean there's 2 mercuries. That means that it has a charge of +2. Remember, that's the oxidation state. So that's the charge, which is +2. Oxygen is -2. So that means it's +2 and -2. It's a 1-to-1 ratio. So that means the formula is this, and that's a solid. I think it's a red salt. It's very pretty. It'd be nice to work with it in the lab, except that mercury is a neurotoxin, so you don't want to do that. Again, you're heating it. And then you're getting liquid mercury. Remember, mercury is a liquid at room temperature. It's the only metal that's a liquid at room temperature. Gallium is almost a liquid at room temperature. It's warm. Its melting point is right at about, where you put it in your hand. It'll actually, gallium will start to melt. Mercury is a liquid, and then oxygen gas. Remember, oxygen is a diatomic. So we balance it. There's a couple different ways to balance it. You could just put a half in front of the O2, or you could double the oxygen and double the mercury, and that would work too. Again, just like we learned, well, actually, be careful. I don't know what Alex is going to say in terms of putting fractions. But we learned back in chapter 5 that it's perfectly appropriate to have fractions in a balanced equation, right? So it should still be. I'm not sure if it is for Alex, but you'll get the same calculation out of both of these because it's the ratios that matter. You're taking the moles of the reactant over the moles of the product. So it's the ratio. So 2/1 is the same as 1/2, right? You just do the arithmetic, you get the same answer. Okay. So now, again, with this one, what do? They give you all this information about the gas, about the oxygen. They tell you it's 58 milliliters. They put it in milliliters just to mess with you a little bit. That's your volume. They tell you the temperature, which is 70 degrees C. And then they tell you the pressure is 1 atmosphere. Right? And then we know that R is 0.082057 atmosphere liters. This time I only went a few more sig figs. There's your R. And then you want to know what N is. Okay. Once you get the number of moles of N, then, or the number of moles of O2, then you got this ratio, whichever one you want to do. I'll do the one with the fraction. You have a half for every one, so it's 1/2. And then you use the molar mass of HGO to figure out what the number of grams is. So in this particular one, they want you to just find the grams of mercury oxide, number of grams. Okay. So let's go through it again. There is this issue, you got this milliliters. So what happens is R is in liters, so be careful. If this is in liters and this is in milliliters, you got a problem. You're gonna have to cancel that milliliter. So let's do this. 58.0 milliliters converted to liters. 1 times 10, oops, sorry. 1 liter is 1 times 10, 1 milliliter. Let me do this. Let's do it from the start. 1 milliliter is 1 times 10 to the minus 3 liters, right? Milliliters. We want to get rid of the milliliters. So 1 times 10 to the minus 3 liters over 1 milliliter. Milliliters cancel, and you get 0.0580 liters. So there's our new volume. Temperature, you got to add the 273.15. So 273.15 plus 70 is 343.15, 343.15, okay? And just like the previous problem is PV over RT, and now we have the right units. So 1 atmosphere, I'll put them in this time. 0.0580 liters, so there's your PV. 0.082057 atmosphere liters per mole Kelvin. And then your temperature, again, you got to add that 273. So that's what? 343.15. Start canceling units, right? Liters. So there you see why the liters got to go. And then you got your Kelvin and Kelvin, and you got 1 over moles, which is moles. Okay. Remember, 1 over X is equal to X. So 1 times 0.05. So it's tricky, you know, like 1 times 0.0580 divided by 0.082057 divided by 343.15. And you get, looks like it's pretty small, right? Yep. I'm going to write in scientific notation 2.0598 times 10 to the minus 3 moles. And this is O2, right? Now, is that a reasonable answer? Well, again, I said that at STP, which is standard temperature and pressure, 0 degrees C and 1 atmosphere, 1 mole has a volume of 22 liters. But this is like very small volume, right? This is 0.05 liters, 0.058. So it should be a pretty small number of moles, okay? Remember Avogadro's law, right? The volume of a gas increases as the number of moles. So if you have a lot of moles, it's going to be a large volume. If you have a small number of moles, it's going to be a small volume. So there's your moles of O2. So 2.0598 times 10 to the minus 3 moles of O2. And the relationship is 1 to 1/2. So 1 mole HGO per 1/2 mole O2. Well, that's a 2 to 1 ratio. 1 to 1/2 is the same as 2 to 1. So you're really going to multiply by 2, right? So I'm going to take that number multiplied by 2. And now I get 4.1196 times 10 to the minus 3 moles. But now it's HGO. And then, now you have to look up, lead is 200.6 is the molar mass of lead, but I don't happen to recall what the molar mass of mercury is. So look it up. Molar mass mercury. So the molar mass of mercury is 200.59. So it's, not that far off from lead. 200.59. Okay. So HGO, 200.59. Oxygen is 16. So that's what? 216.59, right? It's easy. That's grams per mole. So you take your number of moles of mercury oxide, and you multiply by the molar mass. So 216.59 grams for every mole of HGO, right? Molar mass. So now you're going to get a number that's not so small anymore, right? Because you're going to take this 216 and multiply it by that small number. So times 216.59 59. And now you get something not so small. It's almost a gram, 0.892 grams of mercury oxide. There you go, almost a gram, right? So a gram of mercury oxide, if you heat it up and decompose it, you're going to get, at 70 degrees C and 1 atmosphere pressure, you're going to get 58 milliliters, 58 milliliters of water. Okay. And there you go, balanced equation. So there's a couple examples of that. All right, let me see how we're doing here. We are up to gas mixtures now. So let's do a little bit of work on gas mixtures. So section 10.5, gas mixtures. Okay, fun stuff. Okay, so in terms of gas mixtures, imagine that we have, let's say, 3 gases: oxygen, nitrogen, and hydrogen. I like those 3 elements. Let's pick those. So imagine we put all 3 into a container. I'll make this container rigid. So it's like a steel pot. And okay, let's use some colors here. So let's imagine the oxygen are these red ones. Okay. And let's make the nitrogen blue. So we're putting some oxygen and nitrogen into this container. Remember, they're bouncing around, right? They're not just sitting there, they're bouncing around inside. And then we got hydrogen. So let's make the hydrogen, I don't know, I guess we'll do yellow. Hard to see that, I know. I'll put it in there anyways. Okay, they're going to mix together. So it's an interesting aspect of gases. Gases, they mix very freely. So if you put them in the same container, within a few seconds, they're going to be evenly distributed. So you're not going to have like, nitrogen over here and oxygen over there. They're going to migrate very rapidly, very quickly. And that even happens in the Earth's atmosphere, right? So like, if you're breathing air at sea level, oxygen and nitrogen are the main components of air. The composition of nitrogen and oxygen is pretty much the same at sea level as it is if you go 5,000 feet high, up a mile, like Mile High State, like in Denver or something like that, or Mexico City even, right? There's a slight difference, like there is actually a little bit of density difference, because remember, the density of a gas depends on the molar mass. So the greater the molar mass, the more dense the gas is, and dense materials tend to migrate downward via gravity. So in fact, if you looked at, the composition of air at sea level, it is a slight difference than it is if you go up to a high altitude, like 15,000 feet. Not a very big one though, still. And part of that is that oxygen and nitrogen are actually pretty close to each other in molar mass. But in the context of a container, it's a negligible issue. Gravity is a negligible issue. These things are bouncing around. They're perfectly mixed, okay? You get what's called a solution, right? That would actually be a solution because it's so well mixed. It's gases, it's not a liquid, right? It's not like alcohol and water. It's actually gases, but that's the case. That's what you end up with there, okay? Now, if we consider the ideal gas law, PV equals nRT, what the ideal gas law says is it doesn't really matter what the gas is, right? Pressure is something you measure, volume is something you measure, temperature is something you measure, and R is a constant. All that really matters is N, the number of moles. Doesn't matter whether it's O2, N2, or F2. And, again, that's kind of true, but there are some conditions where the ideal gas law breaks down. But for the most part, we can use the ideal gas law for any of these. So I can say this then. What I can do is I can say the pressure of all the gases together, if you add up the pressure of each gas, that is equal to the pressure of the first gas plus the pressure of the second gas plus the pressure of the third gas. And if you had more gases, you would just keep adding them together. And this is often referred to as Dalton's, named after John Dalton, law of partial pressures. Okay. What Dalton's law of partial pressures says is that if you have a mixture of gases, the total pressure of the gases is equal to the sum of the individual pressures. So we could generalize this as the sum of the individual pressures, right? From our first value to our last value. I'll put K. We'll go from 1 to K. K could be 4, 5, 6, whatever, however many gases you want to mix, right? You just add those pressures up. So it's a very simple relationship and it's very useful. Now, keep in mind that we have the ideal gas law. And so what I could do then is I could now say the total pressure, T for total, is nRT over P. Over V for the O2 plus N2RT over V plus NH2RT over V. All I'm doing there is I'm substituting in PV equals nRT. Everywhere that I see P, I substitute in nRT over V. I just divided both sides by V, right? So anywhere where I see P, I just put in nRT over V. Now the N refers to that particular gas, right? So if I'm talking about the pressure of oxygen, it's going to be the moles of oxygen. Now, why isn't it temperature? Why didn't I have to put TO2 or VO2? It's because they're all in the same container. So they all occupy the same volume and they're all at the same temperature. So what does that mean algebraically? If you have things in different terms, but they're the same, you can factor them out, right? So I can actually factor them out and say P sub T for total is equal to, I'm just going to factor out RT over V, right? Because it's in every term, times moles of O2 plus moles of N2. We can't factor these ones out because they're different in each term, plus moles of H2. Now that's an interesting looking form. What that says is if you want to know the total pressure, you just have to know the moles of each of them and then multiply that by RT over V. Again, temperature, you need a thermometer. V, you can just measure the size of the container. So all you got to do is know the moles of them, right? So that's kind of cool. I'm going to go one more step, which is I'm going to say, suppose I want to know the pressure of one of the gases. Relative to the total pressure. So suppose I want to know the pressure of one of the gases. I'm going to take oxygen out of the total pressure. A ratio, right? That would be a ratio. Well, what would you do? Well, you would say, wait, the pressure of O2, I already have that. It's right here. NO2 RT over V. So let's put that in. The total pressure, I already have that too, because that's right here, this one right here. So let's see what you get. Now I'm going to write this down over here. You would have NO2 RT over V. So there's your pressure of the O2 divided by this whole mess down here, right? This one right here. RT over V times the total number of moles. Being a little clever here. Now look what happens. You have RT over V in the top and the bottom, in the numerator and the denominator. So this just simplifies to N of O2 over N total. So let me write that as PO2 over P total. Now this is a nice little relationship here, okay? What this says is the pressure of one gas relative to the total pressure. So let's say, 20%, right? 20% is due to oxygen or 40% is due to oxygen. That's a percentage. All you need to know is the number of moles of each gas. So if you know the moles of the oxygen and the moles of the other two gases, you just take that ratio of moles. So it's the moles of one gas over the total number of moles. Now this right here, we use a name for it. It's called the mole fraction. Why would it be called the mole fraction? It's a fraction, right? It's a ratio. I mean, we could call it mole ratio, but historically it's called mole fraction. It's a fraction. And it's the fraction of one gas over the total, one over the total, right? And so it has a weird symbol. I don't know why it has this symbol, but it has a large X, which is actually the Greek letter psi. And then to indicate that the one in the numerator is O2, we write that as a subscript. Okay. So this means mole fraction of O2. We can expand this and say, look, the mole fraction of N2 would just be the moles of N2 over the total number of moles. And the mole fraction of H2 would just be the number of moles of H2 over the total number of moles. Again, this is for a mixture. So mole fraction is that X, it's a ratio. It's also a form of concentration. How concentrated is the O2 relative to all the gases? How concentrated is the N2 relative to all the gases? So let me show you an example using this. And it says here, you have an 8-liter tank at 29.2 degrees C. It's filled with 12.4 grams of dinitrogen monoxide and 10.4 grams of sulfur hexafluoride gas. These are both gases. You can assume both gases obey the ideal gas law. Find the mole fraction of each of them. Now, they give you the temperature and volume, but you don't need them. To get this mole fraction of each gas, all you need to do is calculate how many moles you have of each gas, and then use our definition of mole fraction as the moles of the gas you're interested in divided by the total number of moles. And you could do this for 3 gases or 2 gases or 6 gases, doesn't matter, okay? So if you look at this problem, they give you the mass. I don't know why this is not working. There we go. They give you the mass of one of the gases. So there's your mass, and they give you the name, so you know the formula. You can find moles from that. Then they give you the mass of the second gas and the form and the name. So you can get the formula from that. So you can get the molar mass from that and find the number of moles. And then you just do your little calculation of mole fraction, moles of the one gas over the total. So let's go through it. Again, you don't need the temperature and volume. This is what we call extraneous information, meaning you don't need it for this calculation. If we were going to find the pressure, maybe we would want to know that, but we don't need it right here. Okay, so let me come over here. So we have 12.4 grams of dinitrogen and 2 monoxide O. Okay. And then you've got 10.4 grams of sulfur hexa. Remember, hexa is 6, hexafluoride. And then we want to find out what the mole fraction is. So let's do the molar mass. So N2, I'm just going to do this right here. 2 nitrogens, 2 times 14.01 plus 1 oxygen, 44.02. Sulfur hexafluoride. So sulfur is 32.07, and then fluorine is 19.00. So that's 146. So let's calculate moles of each. How do we find the moles of a substance if we know its mass and the molar mass? You take mass over molar mass, and that gives you the moles, right? So 12.4 over 44.02. Then you get 0.2817 moles. And then 10.4 over 146.07. And you get 0.0712. Did I get enough sig figs? 1, 2. All right, close enough. So there's your moles. Okay, so now let's do the mole fraction of each. I'm going to do the N2O. You take the moles of the N2O, and then you divide that by the total number of moles. So 0.2817 plus 0.0712. So let's figure out what that is. Actually, you know what I'm going to do? I'm going to figure out what that denominator is. 0.2817 plus 0.0712. So this would be 0.2817. And now the total would be 0.3529. Okay, so now you can do your calculation. Looks like it's going to be about 4/5, about 0.8. So 0.2817 over 0.3529. Yeah, so close to 0.8. So 0.798. No units, moles cancel. So there's your mole fraction of N2O. Okay. In a way, that's telling you that 0.798 of the total gas mixture is due to the N2O. We don't generally do mole fraction percentages or mole percent. You could multiply that by 100 and say, oh, 79.8% of the total gas is N2O. Now, there's a couple different ways you can get SF6. I'm going to show you the longer way. You would take the moles of the SF6 and divide that by the total moles. Now, see why I did the total moles as a separate step in the previous one here? The reason I did that is because I knew I was going to use it again. So 0.0712 over 0.3529, and you get 0.2018 or 0.202. Now, here's another way to do it. Since we're taking 1 over the total twice, they got to add up to 1. So the mole fraction of the mixture of gases, the mole fractions have to add up to 1. So what I could have done is I could have said the mole fraction of SF6 is just 1 minus the mole fraction of N2O. And that would have given me 1 minus 0.798, which would have given me 0.202. You got the same answer as well. Okay, so that works as well. So this is really just the intro problem. It's teaching you how to do the mole fraction calculation, mole of one gas over the total number of moles. But what we really want to do is we want to look at how we use this Dalton's law of partial pressures. So the pressure of one of the gases is equal to the mole fraction of that gas times the total pressure. And that's what we're going to come to on Tuesday. I'll go over that problem on Tuesday. Is you take the mole fraction of the gas you're interested in, multiply that by the total pressure, and that gives you the partial pressure of the particular gas. In fact, let me just do it right now. I mean, we're so close to it. So let me come over here and bring up the problem. Okay. Let me just show you real quick. So calculating the partial pressure in a gas mixture. So again, they give you the temperature, they give you the volume, two gases, they tell you the amount of the gases, just like we did before. And you do the partial pressure, I'm sorry, you do the mole fraction of each. Okay, so that's just like we just did, just a different gas. Then they ask you to find the partial pressure of each gas. Okay, so let me show you how to do this one. We're going to do the first part pretty quickly because we just did a mole fraction problem. So we can do those really quickly, but then I just want to show you how to get the partial pressure and the total pressure out of this. Okay, so I'm going to write all these numbers down and let's take a look. Okay, so our volume is 10.0 liters. Temperature is 20.8 degrees C. If you add that to, if you take 20.8 and you add 273.15, you get 293.95 Kelvin, right? So let's get that into Kelvin so that we've got that. Now here's our two gases. You've got 13.7 grams of dinitrogen difluoride gas. So there's your first gas. You've got 11.1 grams of sulfur hexafluoride. We just did that one, right? Okay, so let's do the same thing we did. We're going to get the mole fraction. So let's figure out the molar mass. We'll do the moles, and then we'll do the mole fraction. X for mole fraction, right? So the molar mass of N2F2 is 2 times 14.01 plus 2 times 19. So that's 66.02 grams per mole. So now to find the number of moles, you take the mass over the moles. So divide that by and get 0.2075. Now we don't have the mole fraction yet, because we need to know the mole. We need to know the moles of the second gas, right? So let's do the SF6. Now the molar mass, we just did that, and it was 146.07. So to find the moles, we take that grams, 11.1, divide that by the molar mass, 146.07, and looks like you get 0.07599 moles. Now we can do the mole fraction. What I'm going to do is N total, 0.2075 moles plus 0.07599 moles. So you get 0.2835 moles. There's your total number of moles. So now you can do the mole fraction, right? The mole fraction is going to be the moles of the gas you're interested divided by the total. So for the N2F2, it'd be 0.2075 divided by 0.2835. So 0.2075 over 0.2835. And that's going to be 0.7319. Remember, the mole fraction is unitless. Okay. Now for the second one, well, that's going to be 0.07599 over the total, 0.2835. Okay, so 0.07599 over 0.2835, 0.268. 0 should add up to pretty close to 1, right? Remember, the mole fraction should add up to 1. So if you add those two together, 0.7319, and add to that 0.2680, you get something really close to 1. It's 0.9999, close enough. We're good to go. So our mole fractions check out. Okay. Now we come back. Now we want to know, we have the mole fractions of each. There's our answer there. We got half of it done. Now we want to know the pressure of each gas. Well, nRT over V. That's all you need to get, if you know the pressure, I'm sorry, if you know the moles and you know R and you know T and you know V, you got your answer right there. So the partial pressure of N2F2 would be nRT over V. So let's put in our 0.7319. I'm not going to do the dimensional analysis. I'll leave that for you. And then our temperature was 293.95. And then our volume was 10.0. Okay. So 0.7319 times 0.082057 times 293.95 divided by 10.0, and you get 1.765. So I'll make that 1.77 atmosphere. Again, you can go through the dimensional analysis to show that that's atmospheres. Now you can do the partial pressure of SF6. Remember, the partial pressure, it just means the pressure of one of the gases. That's all that means. So nRT over V. Of course, this is going to be for SF6. So you're going to use the moles of SF6. Oops. My apologies. I made a mistake here. You want the moles. So not the mole fraction, the moles. 2075. Okay, so let me modify that answer. It's just the moles. So 0.2075 times 0.082057 times 293.95 divided by 10.0. Sorry, 0.501. There we go. Now let's do the second one. You're going to do the moles of SF6, which is right here. So 0.07599 times R, 0.082057 times T, 293.95 divided by V, 10.0. Okay. So 0.07599 times 0.08, oops, 0.07599 times 0.082057 times 293.90. A lot of numbers here, divided by 10.0. All right, does that make sense? That doesn't make sense. Let me check it again. 0.07599 times 0.082057 times 293.95 divided by 10. There we go. That makes more sense. 0.183. So there's your pressure. And that's right there. Now I got, 0.0 something, and I was like, yeah, that doesn't make sense. And the reason I said that was that I looked at this number, 0.2, 0.07. This is about 3 times what that is. And they both have RTV is all the same. RTV. So if this is 1/3 the number of moles, 1/3, 0.07 compared to 0.2, then this should be 1/3 of the pressure. So if I got 0.0 something here, that tells me that's too low for pressure. And then finally, the total pressure, sum of the individual pressures. So that's going to be 0.501 plus 0.183. Okay, so plus 0.501, and it looks like it's about 0.684. There's your total pressure. Okay, so sum of the individual pressures gives you the total pressure. The pressure of each gas is nRT over V. And then, technically I didn't have to use the mole fraction here, right? There is a way to do this problem where you actually do use the mole fraction, but the way they set this up, there's really no need to. So what you could do, typically the mole fraction works like this. The total pressure. You calculate the partial pressure, and then you multiply that by, I'm sorry. The total pressure, you calculate the mole fraction, and that gives you the partial pressure. So that's partial pressure. And then this is total pressure. Okay, same thing here. This is total, and then this is partial. part of the whole. All right. So there you go. So I went through that one. I just wanted to finish that up. It's a little bit longer lecture today, but I wanted to finish that up in case you're working on it over the weekend so that you can get through that whole section. We do have one more section left, which is the kinetic molecular theory of gases. Okay. It's kind of a lengthy set of problems. So I'm going to, on Tuesday, I'll go over that, wrap that up. I'll finish that on Tuesday. And then Wednesday, we'll work on chapter 6. We'll start going into the quantum mechanics. So we're going to go back from 10 to 6 on Wednesday, but I'll spend most of Tuesday talking about the kinetic molecular theory of gases, section 10.6. And then if there is a little bit of time at the end, I'll start doing an intro to chapter 6. Okay. Have a great day.